live. Well, hello everyone at home. Welcome back to another Wednesday evening from Cambridge University Astronomy. We're coming to the end of our season. We just have a couple of evenings after this, so get in while you can. I will say the dates for your diary coming up, if you haven't noticed it yet. As part of the 2022 Cambridge Festival, the Institute of Astronomy is having a public open day on Saturday, April the 9th during the afternoon. So if that seems at all interesting to you, we're going to be putting on all kinds of astronomical games and activities and fun things for people of all ages. So details are on our website if you want to check that out. So on to today's evening, we of course have our normal lineup of a headline speaker followed by some hopefully stargazing if the clouds allow. I say hopefully because the clouds are looking a bit dicey right now. It could go either way. So we're going to have our headline talk and then go and check in with our observers. So yeah, with that, I will introduce our headline speaker. I'm here with Dr Prakriti PalChoudhury, who's going to be telling us all about the Symphony in the intracluster media, which is a fantastic title. And I can't wait to hear what she's going to talk about. So over to you, Prakriti.
Thanks, Matt, for such a nice introduction. And so today I'll talk about Symphony in the intracluster medium. I hope that by the end of this talk, everyone understands a little bit about each of the words used in my title. So when we say the word symphony, what do we immediately imagine? We imagine an orchestra. And as you can see in this picture, there are a lot of people, a lot of musicians playing different kinds of instruments and creating music. So if you look carefully, there are several stringed instruments. And now if I can just remind you about our high school lessons. We studied that a stringed instrument works when we strike a string, we create a lot of waves in that string. Now, fundamentally, this string has a finite length because any given instrument will have a length. When we strike the string, we are essentially triggering different waves. The longest, the biggest length that is possible to be triggered is called the fundamental, which is roughly equal to the length or the size of the instrument. Then you can trigger waves of smaller sizes, particularly the fractions of that length are like the half the length or 1/3 the length. These are called harmonics. So that strikes something in our memory. We know that music is created by notes and there is a fundamental, there are harmonics. And basically what we mean is that we are striking a lot of different kinds of waves. And then the next question is, all is good. We are striking different kinds of waves, but why do we actually hear something in our ears? There are waves. That's all that is good. But what really happens when there are waves and why at all it propagates into the medium? So let us go deeper into this topic. Imagine there is a source of sound and then there is a medium between our ear and there is a length of that medium. What happens when we speak? For example, I am speaking, and if there is a person in front of me, he or she will listen to me. When I speak, I create some vibrations into the air in front of me. And what really happens is that this vibration will slowly spread. So what happens is first the immediate layer is vibrated, and then this vibrates the next layer. And then slowly this vibration just goes out and reaches the ears of the listener. If you notice that when this vibration propagates, the particles sometimes get closer together, sometimes these are far apart because one vibration causes some compression in the medium, and then it takes some time for this to know about this previous vibration and then transfer the news to the next layer, right? Now we want to quantify what happens here. So below I have a wave. It's propagating in one direction. And if you notice carefully, the peak is corresponding to the denser part of the vibration. The trough is corresponding to the rarer part of the medium. What it really means is that the peak of this wave is proportional to how dense the medium becomes locally due to the propagation of that vibration. And that is called the amplitude. The distance between any full peak and the trough is called wavelength, or length of the wave. I was talking about the harmonics and I called the length to be just length, but this is really called wavelength. The time it takes for the vibration to cross this length or this wavelength is called the time period. And when we say that, oh, there is frequency, right? For frequency is always used along with the discussion of waves, right? So what it really means is that given a region, given some time, how many such the peaks and troughs are moving past that region. So that really quantifies how many can actually move. And of course, it will be proportional to the inverse of the time period. So now imagine a very big wave in the sense that the length is very big. So the number of waves that will pass at a given time through a region will be much lower because the length is big, right? The whole peak and the whole trough cannot pass very quickly. So that means the frequency will be low and the wavelength is long. So that's the idea of how wavelength and frequency are related. Now it happens to be so that our human ear can only detect a range of frequencies, which is 20 to 20,000 kilohertz, 20,000 hertz, which basically means that lower frequencies or longer wavelengths are really not something we can detect with our ears. Right? So with this idea, I will get into something a little more complex, like what really happens in a real medium. And I'll slowly take you through the terrestrial sound waves to what we expect in astrophysical objects, which are much bigger, as you can imagine. So the first complexity is that there will be a combination of different kinds of waves. When I was talking about the stringed instruments, I told that we strike the instrument and we generate a lot of waves. These waves will have different kinds of wavelength or length. And what really happens in a realistic setup is that all these waves combine, and these can add up or these can be subtracted, but these combine in a very complicated way. So on the left, I have shown different waves of different lengths. So the biggest length is L, which is basically the wavelength of that wave. And then, as you can imagine from our previous slide, that these are the other waves are really fractional in length of the biggest wave, right? So essentially, when we look into a real system, we expect such a complicated structure from which, if you look at the resultant wave, it's very hard to understand what is the wavelength of that wave, because it has a lot of different kinds of waves. So this is one part of the complexity. The second part is we have different systems of different length scales. So stringed instrument, when I talked about stringed instrument first, it has a finite length because we know the guitar has a finite size, or we know that violin has a finite size. But in reality, can we actually constrain? We kind of can, but this length, the range of these length scales are also very big. On the right-hand side, I show first the Earth. On Earth, we can actually listen to sound, right? There is a range of frequencies or wavelengths that we can hear with our ears. And then, so of course, Earth's size is a good constraint on how big the wavelengths of different waves can be. Now, if we imagine the big picture, the Earth is part of a solar system, which has like 9 planets, and there is a star in the center. So the solar system is much, much bigger compared to the Earth. Then if we think about where the solar system belongs, that belongs to something called a galaxy, which is the Milky Way galaxy. And there is a tiny picture of a spiral galaxy, and the zoom in shows how small the solar system is in that galactic scales, right? So if you imagine what is the fundamental mode of sound wave that we can strike in a galaxy. So imagine the galaxy to be your guitar, and what is the wave that can be created? That's huge, right? Now, where does the galaxy belong in the biggest scales? So that's the background image, which has a very complicated network of dense structures which are connected by filamentary structures, right? That's the universe at the largest scales. And as you can see, the galaxy is a tiny, weeny part of one small dense region. And as you can see, there are several dense regions. I will slowly take you to the astrophysical system that I have named in the title, which is the intracluster medium from this universe scale. Note that there are tiny regions of very, very dense objects in this universe, in the scale of the universe. And each of these objects is basically, it consists of a lot of mass, a lot of gas, which we, just the common gas that we understand, it in fact consists of a lot of hydrogen predominantly. And each of these pockets, there are several. I have just marked one biggest pocket in that network, right? So each of this pocket has lots and lots of mass. And we know on the surface of the Earth, we can feel something that is pulling us towards the Earth, towards the surface, right? And we know that it's the gravity that is pulling us towards, it's a very, very attractive force. Now imagine a billion times stronger gravity. And that's what in each pocket a human being will sense. It's tremendously strong gravity in that one pocket. Now let us zoom into that pocket. So this is a galaxy cluster. That's that pocket, and it's not exactly that pocket, but a pocket which is similar to that. And it has a very strong gravity. It has lots of mass inside it. And this particular one is called Perseus galaxy cluster, which is the favorite of the astronomers, and it has been mostly studied in theory as well as by actual observers. So you can see a lot of different kinds of structures, and you can actually see, if you look carefully, there are wavy structures, there are different kinds of movements of the gas. There are circular movements. There is one big ripple which is going in, and there are some ripples which have clearly gone out, because in the outer region there is a huge circular ripple. So out of this picture, this just imagine taking a snapshot of something. And it happens to be so that this is not in the visible range, unlike the conventional photography that we do on Earth. This is in the X-ray range. And this is just a snapshot of a galaxy cluster. And what astronomers have done is they have tracked down the ripples, and they have found several such ripples all over the medium. In addition, we also know from the same picture that there are two very interesting structures in the center, as you can see. These are called cavities. What cavity really means is that there is less amount of matter in it. There is less, it's low density region, and it is bimodal. There are two bimodal low density regions. Now in the center, there is always a supermassive black hole. It's extremely strong gravity. Imagine something which is much, much stronger, strongest gravity in the universe. So that's the central black hole. Now on top, as I was saying, there are two cavities which are low density, but even then, these cavities are maintaining these structures. This is very coherent, which means even if this is low density, there is a very strong pressure that is keeping the structure intact. it also basically means that if there is a strong pressure, there is a strong thermal energy. Microscopically speaking, particles are moving very, very fast, and that's expressed in the macroscopic scale as a strong, as a very high energy region, which is very hot in temperature and which is exerting a lot of pressure on the surrounding medium. Now, what these cavities do is the cavities actually move around a little bit. These vibrate. And now let me remind in the first slide, in the second slide, I showed that there is a source of sound, and then that when it creates some vibration, these vibration just propagates out into the medium. So something very similar happens here. These cavities are vibrating, and then these are creating ripples. And at one go, these ripples will take some energy of this immensely concentrated source of energy, and these are basically carried away into the medium. So cumulatively speaking, actually these sound waves can carry out a lot of energy from that concentrated energy source into the medium. Now, one interesting question that you can ask is, we are essentially putting a lot of, we now know that there is a lot of energy in that concentrated cavities. And we also know that sound waves are taking some of this energy and depositing it somewhere out into the galaxy cluster medium. So why is this cluster still intact? Why is this not being blown away? And this is a very interesting question in galaxy cluster research, and a lot of theorists and astronomers are looking into this problem. So what really happens is, as I mentioned, whenever there is a high temperature gas or high energy gas, that means microscopically, all the particles are moving around very fast. And every time a fast electron passes through a medium closely at a short distance with a positive charge, it actually gets deviated a little bit, which means it is actually slowed down. So that all that kinetic energy that it was carrying is not there with the electron anymore, and some of this energy is being carried away by radiation. This is what is the X-ray radiation that we observe. There is a very scary name here, which is called bremsstrahlung. There is nothing to be scared about it. It basically means braking radiation, which means braking, which is like the car brake, which is actually slowing down the motion of the electron. So that's why it's called a braking radiation. So electron is slowed down, and that fractional energy is of the electron, which is lost because it's slowing down, is basically into the X-ray emission. And that is what we are observing when we say that, okay, this is the Perseus galaxy cluster. So all these bright spots are where this emission is strong. And now that answer is also in front of you. So before this, I was telling you that there is the very good source of energy that's heating the medium. Sound waves are going out and depositing some amount of energy, but this medium is not blowing apart because this medium is also releasing out some energy. And on an average, we know now that this release of energy by the braking radiation is roughly balanced by that heat that is being deposited by the sound waves, or generally by the cavities that we see in the center. So that's about cooling, and that's about the thermal balance. I will quickly show some other similar galaxy clusters. These are all observed in the X-rays. So this is the Coma cluster, and the central red region is the X-ray emission. You can actually see the optical, which is the stars. This is very similar to what we see when we look up into the night sky. These are all the stars in that embedded in that gaseous medium. This is the bullet cluster. This is also very interesting and similar to the other one. The reddish region is the X-ray emission from the center. There are optical emission from all the stars that are embedded, something very peculiar is that this is essentially merging of two clusters, two such big galaxy clusters. And you can see that there is a jutting of X-ray region. There is a triangular shaped region away from the center, which basically means one cluster has gone through the center of the other cluster. So all that is kind of very exciting, and we can astronomers can actually observe all of these with the telescopes. So now that we have talked about real clusters, now you know what intracluster medium is, what galaxy cluster is. Essentially, intracluster medium is the gas that is inside galaxy clusters. Galaxy clusters are these pockets of gas in the big picture of the universe. It has very strong gravity. All the big picture is now there. So we now zoom in a bit more. I talked to you about ripples going out, or the sound waves that are there, which are generated by vibrations in the center, right? But if you look carefully, there is a different kind of motion in that. When we think about sound waves are really going out. These are these vibrations that are generated in the source, and these are essentially propagating out like this radially. But in addition to that radial movement, there are also these very circular kind of movements, if you look carefully into the finer structures there. And there is something funny about this circular movement. If there is a vortex, a big vortex, which has a very high velocity, then something very peculiar happens. The vortex transfers that kinetic energy or the high velocity to smaller vortices. And then the smaller vortices transfer that kinetic energy to even smaller vortices. And thus, if there is high kinetic energy in a big vortice or a series of big vortices, then all that energy is transferred, and you basically can see a range of different sized vortices eventually. But all this happens if the velocity of the big vortex is very high. Something incredibly peculiar happens even if the velocities in the medium are not that high. It's a peculiar kind of wave. Just to give a very rough analogy of what this is about, imagine a road which is very, very blocked because of the traffic, and all the cars are stuck in the traffic signal. And then none of the cars can actually move because there is a signal and all the cars are lined up. So there are two roads here. On the left, there is one road where the cars are very nicely lined up actually. And on this side also there is a lineup, but this is a little more haphazard, the central circular region, right? So what is happening here is that the cars cannot move straight into that lined up medium, right? Because things are very tight in that direction. So cars are taking a strange kind of, it is turning in different directions. And these cars are trying to sort of get out of this stuck up situation as fast as possible. So these cars are basically turning in all possible directions, right? So something like that happens in a medium like galaxy cluster when there is a very strong gravity, which is the central gravity, as I told before. So here on the left, I will demonstrate this, this peculiar wave. Note that this is like a small chunk of galaxy cluster where the gravity is downwards. And if you look carefully, there is some kind of wave which is there. You immediately you cannot figure out what is going on. But if you look carefully, there are stripes, which are like single waves, because the black region is like a trough and the blue region is like a crest. I was talking about crest and trough at the very beginning. So you'll note that, I'm just playing the video again. You'll note that all the troughs and crests are moving in this direction, while the entire bulk movement is happening in this direction, which is very strange, right? Because we know of sound waves where troughs and crests are moving in this direction and the bulk movement is also happening in the same direction. So this kind of motion, which is very similar to traffic jam, because all the gas layers, which is along the gravity, these layers are sort of tightly constrained to move because gravity is pushing these layers down and the gas pressure is keeping them intact against gravity. So there is not much chance to move around from that stability. Now, if there is a small amount of perturbation on that stable medium, this cannot go out very freely, right? So this happens like a bulk movement in the perpendicular direction of the gravity, which is like the perpendicular plane if the gravity is downwards. So this can also create vortex in the medium but these are very small vortices in the sense that the velocities are very small. So these can also generate the circular motions that I was talking about before. So now, basically, just to tie up everything, I have talked about waves, which are essentially the sound waves, and I have talked about how we cannot imagine a simple sound wave in a complicated medium like galaxy cluster or any astrophysical system. Sound waves will have finer structures because a lot of waves will sort of get combined by addition or subtraction, and that will create some finer structures on the large scale wave. Then I talked about circular motions, and I talked about two kinds of circular motions, right? One where there is a lot of velocity in a big vortex, and this big vortex can transfer this velocity to smaller vortices. So this is one kind of circular motion or vortical motions. I talked about a different kind of circular motions which come from a different kind of wave, a very peculiar wave, which does not propagate in the same direction as the troughs and crests, right? So the bulk movement happens perpendicular to it, which causes circular motions in a real system. Now, if we want to sort of model such a system, like I am a theorist and I want to sort of study such a system in terms of equations, what we really do is we model such a system writing a code for it, and we put that in very big computers, in fact, multiple computers connected together, and we try to study such features across time. Because I told you that when we look at a cluster in the X-ray, we are essentially taking a snapshot. It's an image which is frozen in time. We do not really know how such features are moving around. And as modelers or as theorists, we want to know how such features evolve with time. And this is a very complex simulation. As you can see, that something crazy is going on, right? So I'll just quickly give pointer to what this all means. So this, in the very central region, there is a galaxy cluster. And what we are looking into is the velocities in that medium. So this square is like a significant portion of the galaxy cluster. And as you can see, there is a huge circular thing coming out. This is essentially the sound wave, which is generated in the center due to the heating. I explained the kind of vibrations that are generated due to the presence of cavities there. And this is like one such model of sound waves, which is spreading out into the medium. In fact, it is also taking energy from the center and putting it in the outskirts. On the right, I have separated out the kind of velocities that create circular motion. So as you can see, the resultant circular motions are actually generate a very, very complex medium. There are lots of things are happening. So big vortices are giving rise to small vortices. Then there are some peculiar waves being generated, the kind of waves that I talked about, which is similar to the traffic jam. So it cannot go in the direction of gravity, which is radial. So it spreads out in the perpendicular direction, which is like along the circumference of the circles that you can draw on this. And as a result, there is a very complex scenario created in the center. And this is what we essentially do as models in astrophysics. And this is how we study such a system. So with this, I will kind of go to summarize everything that I mentioned so far. If you remember, I told you, I promised that my title is Symphony in the Intracluster Medium. So symphony means there will be lots of different kinds of vibrations, different kinds of oscillations and waves, the primary one being the sound wave. But we also have different kinds of circular motions. And now we know there are some peculiar waves generated in the presence of gravity, which can cause circular motions. Then we also know that if there is a lot of velocity, that is, if the medium is very disturbed, then big vortex with a high velocity will generate small vortices, and that will create some more complex structures in the medium. So I have gone back to my favorite and I think the most beautiful picture of the galaxy cluster, of Perseus cluster, and finer structures there, just to remind like what we had in mind when we started off. And here let us note that it's not just galaxy clusters where such waves are studied. Also stellar interiors, particularly sun, is a place where a lot of solar physicists look into such wave structures and what kind of oscillations are generated in the wave. One example I have given, the arcs are sort of the kind of sound waves that are generated within sun, and these get reflected back and forth. So it creates very complicated structures inside the sun. And so basically the universe has a lot of music, which we cannot hear because it's a much lower frequency. As you now know that the length scales are much bigger than the conventional sound waves that we can hear in our ears. The next question is, what is the future direction? Like, how is this evolving? What are the things that we look forward to? So one thing is that all the galaxy cluster pictures that I have shown in this talk are from two most well-known telescopes, Chandra and the XMM Newton. The next future mission is, one of them is LINX, where you can actually better understand the structures, the finer structures, because you can really sort of zoom into what kind of finer details are there in the medium, in the observable X-ray medium. And then you will know like what is exactly the nature of the wave that is there, wave or oscillations or circular motions, anything. So that's the future. For us, like theorists, for theorists like me, we look forward to what astronomers have to tell us about generally such a system, like what kind of temperatures the gas has in the galaxy clusters, what is the gravity, and what do we know about the different features. For example, I modeled the sound waves, taking cue from astronomers that there could be sound waves in that medium. And what we really do is we time evolve such features, and we want to understand how such features evolve in a shorter span of time, because from observations, we really cannot say anything about the time evolution of different kinds of features, right? So we just take a snapshot of a system. And then we just get hints that these are the kind of features that could be there. As theorists, we try to model them and we try to time evolve them. And basically this kind of work requires high performance computing and extremely parallel codes, which basically means a lot of computers run parallelly and basically run different parts of the code, and then give the full model of galaxy clusters or any such astrophysical system. So on that note, I will finish. Thank you so much for your patience, and I will take questions.
Prakriti, thank you so much. A really fascinating subject. The YouTube chat box is down there if anyone that wants to ask a question. I might kick us off by asking, you have that lovely video of that simulation of what was going on, and there was some red stuff and some blue stuff. Can you describe what the red and the blue means?
So these are, I think I mentioned that these are velocities in the medium. So red is positive, blue is negative. Positive means that in any x, y direction, positive is going along the positive x direction, negative is going in the negative x direction, and similarly for other y and z direction. So basically it is a complex velocity structure in the medium.
Wonderful. Okay. Well, so my YouTube is telling me there's a bit of a delay in the stream, so I think we've just asked for questions, but I think it might be a couple of minutes until it actually goes out there. So maybe the best thing to do is wrap it up, because I think I've heard from our observers that things are looking very wet and not all no stargazing possible, unfortunately. So I think with that, I will thank our main speaker, Dr. Prakriti PalChoudhury, for giving us such a wonderful talk and such a wonderful view into the way we do these simulations. And come back next week. We have 2 more of these evenings left before the end of the season, and then leading up to Saturday, April the 9th, the Institute of Astronomy and Kavli Institute for Cosmology Open Day, and there's more information about that on our website. So we will see you next week.
Thank you so much.